So this is section 3.6 of the text. So we'll call this lecture number 3, section 6. Part 6. Okay. And in this lecture, we'll talk about derivatives of logarithmic functions. All right, so this will be the last section that we'll talk about, which will cover exam 3.1. So exam 3.1 will include this lecture, up to this lecture. All right, so let's see, what do we have here? So we know the equation of a log. This is the log, right? Log base A of x. And of course, we're making the assumption that A is greater than 0 and A is not 1. Okay? And so if y is equal to log base A of x, we can solve for x like this. So A to the y is equal to x, right? So our objective here is to calculate the derivative of the log function. All right, so we know we basically want what? For this equation, we want dy over dx. So what is the derivative? Okay, and we can use this to solve it. So we know the derivative of the exponential function. The derivative of the exponential function is a to the y times the natural log of the base times the derivative with respect to x of the exponent, which is dy over dx. Okay, and if we differentiate both sides, we get 1. So now we just solve for dy over dx. So dy over dx, okay, that's equal to what? 1 divided by a to the y times the natural log of a. Okay, and we know that a to the y is x, right? So that would just be 1 over x times the natural log of a. Okay, and if a is equal to e, which is approximately equal to 2.71828, okay, we have the derivative of y with respect to x is equal to the derivative of the natural log function with respect to x, which is equal to 1 over x times the natural log of e. And we know that e and natural log are inverse functions. The natural log of e is 1, so that's just 1 over x. So we now have a formula for the derivative of the natural log function. Okay, so how about log base 10? So if we have y is equal to log x, where the base is presumed to be 10, so we have y prime would equal to 1 over the natural log of 10 times x. Okay, so that's the derivative of the natural log function. Okay, so that's it. That's pretty much it. Now there's some nice problems that can come from this. So how about y is equal to, say, the natural log of the sine function? We want to calculate its derivative, so we'll have to use the chain rule for this. So y prime is equal to 1 over sine x, okay, times the derivative with respect to x of sine x, which is equal to cosine x over sine x, which is equal to cotangent x. Okay, so the cotangent function is a derivative of the natural log of sine x. Because remember, how did I get this? Remember, to calculate the derivative of a log function, it's 1 over the argument to the log function, in this case sin x, times the natural log of the base, in this case it was e, times the derivative of the function. So we have a useful formula for calculating the derivative of the natural log of a function. Okay, and this is a handy formula. I would suggest keeping, kind of memorizing it in a sense. Okay, if we have this, the derivative of the natural log of a function is the derivative of the function divided by the function. Okay, and if we have something like y is equal to log base b of a function, where b is not the e, then its derivative would be the derivative of f of x divided by the function times the log times the natural log of b. Okay, so we have that. All right. So how about let's calculate the derivative of the square root of the natural log function. So y prime would equal to 1/2 times the natural log function to the negative 1/2 times the derivative of the natural log function, which is 1 over x. So that's equal to 1 divided by 2x times the square root of the natural log function. Okay, so you can do these like so. How about f of x is equal to log of 2 plus sine x. Okay, and so if we use the formula, it'll be the derivative of the argument to the log function, which is cosine x, divided by the function itself, times the natural log of the base, which is 10. It should be a 10. Okay. All right. What else? Okay, so let's have a piecewise defined function. So how about if f of x is equal to this? Natural log of x, if x is greater than 0, and the natural log of minus x, if x is less than 0. So what is the derivative for this function? Okay, so that would say that f prime of x would be piecewise defined also. So that would be 1 over x for x greater than 0, and 1 over negative x times a negative 1, which is equal to 1 over x if x less than 0. Okay, so it's basically equal to 1 over x for x not 0. Okay, so there are some advantages to using logarithmic differentiation. So for instance, consider this obscene looking function. How about y is equal to x to the 3/4 times the square root of x squared plus 1 divided by 3x plus 2 to the 5th. Okay, so we want to calculate the derivative of this function. Now, obviously, we don't want to have to use the quotient rule for differentiation for this. This would be really tough. So a technique, an efficient technique, would be to take the natural log of both sides. And so if you're proficient in knowing how to do logarithmic expansions, we can readily see that the natural log of y is equal to the natural log of x to the 3/4 plus, recall that the natural log of a product, remember the natural log of a product? It's equal to the natural log of a plus the natural log of b, okay? And then the natural log of a quotient, like this, is equal to the natural log of c minus the natural log of d. So we're going to use these facts to solve this problem. Okay, so here in the numerator we have a product, so the natural log of 3/4 times the natural log of x squared plus 1, and then minus the natural log of 3x plus 2 to the 5th. So we can further continue our logarithmic expansion. Okay, remember the exponent of a function in a log can become the coefficient. Okay, so this would be 3/4 times the natural log of x plus 1/2 times the natural log of x squared plus 1 minus 5 times the natural log of 3x plus 2. Okay, so that's the natural log of y. Now, so all we have to do is differentiate both sides with respect to x. So on the left-hand side, we'll have y prime over y, okay, is equal to, because remember, the derivative with respect to x of the natural log of a function is the derivative of the function divided by the function. Okay, so y prime over y is equal to 3/4 times 1 over x plus 1/2. Okay, so the derivative of x squared plus 1 is 2x divided by the function itself minus 5. Derivative of 3x plus 2 is 3 divided by 3x plus 2. Okay, and so we can simplify the right-hand side a little bit. So that would be 3 over 4x plus x over x squared plus 1 minus 15 divided by 3x plus 2. Okay, and now, so all we do is solve for y prime. So y prime is equal to 3 over 4x plus x over x squared plus 1 minus 15 times 3x plus 2 times y. So we replace y with its definition in x. So this would equal to 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And y is, what was y? Y was x to the 3/4 times the square root of x squared plus 1 divided by 3x plus 2 to the 5th. So had you decided to use the quotient rule for differentiation, I doubt very seriously if you would obtain this result in a brief amount of time that it took to solve it this way. All right. Okay, so now we can prove, do you remember the rule earlier on in the lecture sequence where we were trying to prove what the derivative of x to the n was? And we sort of punted and said that n could be any number. And so y prime is equal to n times x to the n minus 1, where n is any number, and we couldn't come up with a substantive proof for that. Well, now we can. Now we can use logarithmic differentiation. So we know that the natural log of y, okay, let's take the absolute value in case y is negative. The natural log of the absolute value of y is equal to the natural log of the absolute value of x to the n, like so. And that's to guard against negative numbers, because we can't stick negative numbers into the natural log function. And so using the logarithmic expansion, we have this, okay, where obviously x cannot be 0. Okay, so now what do? So we can take the derivative with respect to x for both functions. So this becomes y prime over y. Okay, and notice the absolute value bars go away. And so this would equal to n over x. Okay, so I've taken away the absolute value bars. So now we solve for y prime, so y prime is equal to ny over x, and y is equal to x to the n, right? Okay, and using the laws of exponents, we get x to the n minus 1. So there's a cheap and easy proof for the power rule for differentiation. All right, so what else? What other kind of trouble can we start? Oh, okay, so let's do an example. How about we take the derivative of this exponential function, x to the square root of x. So we want y prime. Okay, so again, using logarithmic differentiation, I'm going to take the natural log of both sides. Okay, and then use logarithmic expansion. Okay, and now all I have to do is differentiate both sides. Okay, so the derivative of natural log of y is y prime over y, and then I have to use the product rule for differentiation here. So that would be the first function times the derivative with respect to x of the second function, plus the derivative of the first function times the second function. Okay, and so y prime therefore is equal to the square root of x times 1 over x plus 1/2 times x to the negative 1/2 of x, times the natural log of x, and y is what? X to the square root of x. So there's the derivative of, I guess we could simplify this, so this would be 1 over x to the 1/2 plus 1/2, 1 over 2x to the 1/2 times the natural log of x times x to the square root of x. Okay, and that can probably be simplified even further. You can factor out 1 over x to the 1/2 and so on. Okay, but there it is. I think you get the point. Okay, so let's see what else we can talk about. Okay, the number e. Okay, let's talk about how we can get an expression for e. Where does the number e come from? Okay, well, we can use logarithmic differentiation to find the value of e. So this will be the next problem. Find the value for e. Well, we've already seen one case where we could find the value of e when we calculated the derivatives of exponential functions. But here's a cleaner way of finding a value of e. Okay, so it starts out this way. Let's let f of x equal to the natural log of x. Okay, then f prime of x is equal to 1 over x, like so. Okay, so what is f prime of 1? Okay, so we know f prime of 1, okay, is equal to, in terms of the difference quotients, okay, so we'll bring that back again. That's the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. Okay, now what I'm going to do is I'm going to replace h with x. So let's do that. So the limit as x approaches 0 of f of 1 plus x minus f of 1 divided by x in terms of x. Okay, so now I'm going to replace f with its definition, which is the natural log. So that would be the limit as x approaches 0 of the natural log of 1 plus x minus the natural log of 1 over x. And we know that the natural log of 1 is 0, so that goes away in the numerator. Because remember, Recall the graph of the natural log function. It's asymptotic with the negative x-axis, and it has an x-intercept at 1, 0. Okay, so this is y is equal to natural log function. Okay, so don't forget that. Don't ever forget that. So continuing on with our problem solution. So we have the limit as x approaches 0 of 1 over x times the natural log of 1 plus x. Okay, which, now using the logarithmic contraction properties, the limit as x approaches 0 of the natural log of 1 plus x to the 1 over x, which we know that f prime of 1 is equal to 1, right? We just plug in x equals 1. So we have this limit, the limit as x approaches 0 of the natural log of 1 plus x to the 1 over x has to equal to 1. Okay, so what do I do next? All right, so the next thing I'm going to do is I'm going to use a limit law situation. I'm going to consider each side of this equation as an exponent to e. Okay, so I have e to the limit as x approaches 0 of the natural log of 1 plus x to the 1 over x is equal to e. All right, now what I can do is we can use the limit laws here, one that I kind of glossed over at the outset. Since this function, the natural log of 1 plus x to the 1 over x, is continuous on its domain, okay, it's continuous on its domain, we can take the function e to the x and we can bring it inside the limit operator. So we can interchange the base with the limit operator since the exponent is a continuous function, and that's a limit operator. So what we have is we interchange the base of the exponential function with the limit operator because the exponent is continuous. So we have 1 plus x to the 1 over x is equal to e. Now, we know that e to the natural log of x, since e and the natural log function are inverse functions, that's equal to x by the inverse function property. And so we have the limit as x approaches 0. So the e and the ln annihilate each other. 1 plus x to the 1 over x is equal to e. Okay, and so this is where e comes from. Okay, plug in smaller and smaller values for x, and you'll get a value for e. So because x never equals to 0, see x never equals 0 by the limit operator, that's why e is an irrational number. So you see the construction of an irrational number. All right, so we can do some fanciful things here. We can choose a change of index for the limit operator. So let's say let n equal to 1 over x. Okay, so if x goes to 0, then 1 over x gets very, very large, and n has to go toward infinity. Okay, like so. So e then, expressed as an infinite limit, would equal to the limit as n approaches infinity, and n is equal to 1 over x, so this would be 1 plus 1 over n to the nth power. Okay, so this is okay, and of course, bear in mind that we have that. Okay, so technically speaking, x approaches 0 from the right. All right, so we can do a problem now. We can do some more fanciful limit problems. How about the limit as n approaches infinity? We want to evaluate this limit of 1 plus x over n to the nth power. So what does that equal to? Okay, well, what we can do is we can do some manipulations. We need to replace, obviously, x over n with a variable. So let's say, because if we replace x over n with a variable, we can exploit the use of the results from, we can use these results right here. We can use this result. Okay. So let's try and reformulate the problem in terms of this style right here. Right? So the way we can deal with that is we say, let's let m equal to n over x. Okay? And so 1 over m is equal to x over n. All right? And let's see, as n approaches infinity, m approaches infinity for a given value of x. Okay? And let's see what else we have. Okay, so n is equal to mx. Okay? So let's make the substitutions in terms of m. So the problem becomes now, okay, instead of n, we'll use m. So m goes to infinity. 1 plus now x over n is what? X over n is 1 over m. And then x is, no, n is equal to mx. So we have mx. Right? And then we can readily use our laws of exponents to simplify this now. So this would be the limit as n approaches, no, m approaches infinity of 1 plus 1 over m to the m power to the x power, like so. We can factor the exponent. And so this is equal to the limit as m approaches infinity. Let's see here. Actually, I can move the brackets further out because since x is not partaking in the limit, we can move the brackets out. So let me readjust this. So we can say this is equal to the limit. By the limit laws, we can take x out of the limit operation. This would be 1 plus 1 over m to the mth power, okay? All of this to the x, okay? So remember the limit law. The limit of a function raised to a power, okay, is, okay, it goes like this. Remember, recall the limit law. The limit of a function raised to a power, okay, is equal to the limit, oops, extend page, is equal to the limit of the function, okay, raised to the power. So we can do that. So that's what's going on here. So we can put our x there, right? So by the limit law. So another application of the limit laws. And then if you recognize what's inside of brackets from the previous slide, that's simply e, right? So the expression then is equal to e, which in brackets, to the x. So now we have a formula for e to the x. So this is, e to the x is actually this limit. Okay, it's that limit. All right, so that closes out, or does it? No, let's see, do we have some more stuff to do? Yes, we do have some more stuff to do. Yeah, a couple of more examples I think we should consider. Okay, so how about we use a chain rule problem here with logarithmic differentiation. Suppose my exponent is cosine x, x to the cosine x. So what is the derivative of this function? So natural log of y is equal to the natural log of x to the cosine x, which is equal to, by logarithmic expansion, cosine x natural log of x. So using the rubric, the natural log of a function is the derivative of the function divided by the function. And then we use what? Take the derivative of this, so that would be the product rule for differentiation. And we know the derivative of the cosine function is minus sine function. And then we just solve for y prime. So y prime is equal to let's see here. Is that okay? Did I do that right? Cosine x? Yeah, that's correct. Okay. So y prime is equal to cosine x times 1 over x minus sine x times the natural log of x times y, which is x to the cosine x. Okay, yeah, so that's the answer. Yeah, so there's the answer. Okay, yeah, yep. Okay, another problem. How about f of x? So let's calculate the derivative of this function. F of x is equal to the natural log of the natural log of the natural log of x. Okay, so f prime of x, start with the outer function. Okay, so that would be the derivative with respect to x of the natural log of x, all divided by the function itself. Okay, and so we have to fix the numerator. So that would be the derivative of the natural log function divided by the natural log function, right? Because we're taking the derivative of the natural log of this function divided by the natural log of x. And so that's it, right? So that would just be 1 over x times the natural log of x times the natural log of x. Okay, so right there. Okay. And what would the domain of f be, by the way? Okay, so the domain of the function, that's an interesting problem. The domain of f would be x such that the natural log of x has to be greater than 0. Okay, and that would have to be set x such that what? Well, the only way the natural log can be greater than 0 is if its argument is greater than 1. So that would mean that the natural log, this natural log right here, would have to be greater than 1. Because remember, the natural log function is only greater than 0 if x is greater than 1. And so in this case, our x is not x, but natural log of x. So we have that. And so this would imply to set x such that what? X has to be greater than e. So that's your domain. Interesting, rather peculiar result. Okay, and so finally, the last example for this section, we want to calculate the derivative of y is equal to log base 2 of e to the minus x cosine pi x. Okay, and so the derivative, okay, is the derivative of the argument. So that would be, you have to use the product rule. So let me put a placeholder for that. That would be the derivative with respect to x of e to the minus x cosine pi x. It's a cosine pi x. Okay, divided by the natural log of 2 times e to the minus x cosine pi x. So all we have to do is fix the numerator. So we'll have to use the product rule for differentiation. So that would be e to the minus x times pi times a negative sine pi x by the chain rule, and then minus e to the minus x times cosine pi x, okay, divided by the natural log of 2 times e to the minus x cosine pi x. Okay, and so we can get some cancellations going on. This cancels, this cancels, this cancels. So yeah, so that would be your answer. Oh wait, that's okay. So that would be y prime over y, right? Let's see. No. That's right. That's right. That's right. Yeah. Okay, so that's one way of doing it. Another way, of course, is you could use the logarithmic expansion. So let's try the alternative approach. So we know that y is equal to log base 2 of e to the minus x. Okay. Plus log base 2 of cosine pi x. So y prime then would equal to what? The derivative of the function, which is minus e to the minus x. Oh, what was that? Something happened. So that would be minus e to the minus x over natural log of 2 times e to the minus x. Okay, we could say that. What else? Yeah, plus a minus pi sine pi x over cosine pi x. Cosine pi x times the natural log of 2. Okay, and let's see. Yeah. Okay. Let's see. Okay, yeah, we can go with that. Another way we could deal with this also is note that log base 2 of e to the minus x is equal to minus x times the log base 2 of e, and so its derivative. So if we were to calculate its derivative, we would have minus log base 2 of e. That's another way of saying it, which is negative 1 over the natural log of 2. So you can play these games as well. All right. So this is the conclusion of the material needed for exam 3.1. So I'm hoping that you've got your web assignments up to date and that you're working diligently on those. And I believe at this point you should have enough material. Well, not quite. You should start looking at your project number 3. Your project number 3, of course, will be due on the first class day prior to exam 3.2. So go ahead and start looking at exam 3.2. And as always, if you have any questions, please see me or write to me. Okay, so that concludes this lecture.